from prerequisites that I'm not only expecting you to know, but that would be very helpful for this class. So pay attention, take a look at this. Anything that is in this list that we cover that you feel like you maybe don't quite know as well as you should, spend some time this week reviewing. In fact, that first homework assignment itself is a bunch of prerequisite review. There's a bunch of prerequisite review in that homework assignment, as well as one or two things from our first chapter that we'll be discussing today, on Wednesday, and maybe a little bit on Monday. There will be some cases of problems that we might not talk about until the Monday that assignment is due. In that case, just pay close attention to those problem identifiers so you know where we are. But we're going to start by discussing algebra. Then we'll discuss some function stuff. We'll kind of do both of these together. And then we'll spend some time on geometry and trigonometry. Geometry, specifically linear functions, is a major topic for Calc 1 because we're going to be using linear functions quite a bit. As well as I like this idea of creating a catalog of essential functions for math in general. We're going to create a catalog of the functions whose behavior I'd expect that you know without a calculator. In this case, this is probably the most helpful review if you don't use a graphing calculator for this class. As well as we'll add trig functions to our catalog, and we will spend a little bit of time with the unit circle. Daniel and I have some great resources for reviewing trigonometry. There's some as well posted in Canvas, but if you find yourself struggling there, do reach out and let us know. And I did post a picture of the unit circle on this document. In fact, the unit circle is the one thing that you're free and clear to use on tests. I don't mind that at all. I myself don't even have it memorized outside of the first unit or first quadrant. So I will allow you to use a unit circle on the test. So let's get started. Let's make a catalog of essential functions that we need to know for this class and really for just about every math moving forward at this point. A linear function. And this catalog of functions I'll refer to as a catalog. I may even refer to the specifics as parent functions. The function f of x equals x is the parent function of the linear function. It's the basic linear function that you can graph, and it's the one that you should think of if you're ever dealing with a shifted and scaled linear function for whatever reason. It, of course, looks like this. It's a line with rate of change 1 passing through the origin. The y-intercept of that parent function is 0. We are passing through the origin in that case. Let me get my notes out here so I can remember exactly everything I wanted to say about all these things. An example of a linear function that's not the y equals x function is something like f of x equals x plus 2. F of x equals minus 2x minus 1. Really, in general, a linear function has the form y equals mx plus b, where remember that m is the slope and b is the y-intercept. We'll discuss a little bit more about this when we get into the geometry section, but a linear function essentially looks like this. We have a factor of x. There's no power on x here. S is x to the 1, x to the first power. This would be a linear function. But if we increase the degree of that variable x to 2 or 3 or more, we have a polynomial, a quadratic, or a cubic. Yes, I use Notability. Amanda, this is the Notability app. It looks like this.
Yeah,
this is the
posted the
icon.
wrong link. I'll fix it later. I searched the wrong name. Or I'll paste it now.
It's Notability. It is a paid app, though. I think it's like $10. But I've gotten so much use out of this app. It's the best $10 I ever spent. So if you have $10, I'd recommend it. I believe that OneNote, you can get OneNote as an app for free and use that as well.
That works well.
If we increase the degree of x to 2, we have a quadratic function. I actually really watched a really cool number file video yesterday about quadratics. Quadratic functions have a shape like this. What this shape mimics, and the reason the shape was created, was to model things like, or to discuss things like trajectories of like objects in the air. This is the first person who dealt with quadratics, was interested in, if I'm standing here and I throw a ball, what happens to it? So the quadratic function, y equals x squared, shifted and scaled in the plane, could potentially model the path of a thrown object, a trajectory of an object being thrown. The parent function, f of x equals x squared, looks like this. It's a quadratic opening upward with vertex at the origin. And the vertex is the point of interest here for shifting and scaling this quadratic. But some examples of quadratic functions, anything with an x squared in it essentially is a quadratic function. You could see it written like this. This is a quadratic function. As well as you could even have something like this. Notice this coefficient here. That is important when shifting and scaling this parent function, y equals x squared. As well as you can see quadratic functions written like this as well. That's very explicitly a quadratic function. You see that x squared there. This relies on a little bit of foiling to be absolutely certain algebraically, but these are all quadratics. You can turn any quadratic in this form into a quadratic that explicitly states the vertex by completing the square. So this is one topic that could be useful in this situation. Completing the square puts the quadratic in a form where the vertex is written. In this case, the vertex is -2, -3. The vertex is located at negative the value here, and the y-coordinate is that value there. We'll talk about that a little more when we do shifting and scaling, but the quadratic function is the function that I like to use as the base case if I ever forget how to shift and scale, because I know how to shift and scale this guy. If I ever forget shifting and scaling, I'll think back to the quadratic function and ask myself, how do I shift and scale this function? And we'll talk about that in our shifting and scaling section. As well as cubic polynomials. Granted, there exist polynomials of degree higher than 3, right? There's 4th degree polynomials, 5th degree polynomials, 8th degree polynomials, 100th degree polynomials. But the quadratic and the cubic are the two that we consider the parent functions of the quadratics, or the polynomials. The quadratic function being of order 2, all polynomials of even degree are going to have in behavior that matches this parent function. All polynomials of odd degree are going to have in behavior that matches this cubic function. The shape of them might be a little bit different, but the in behavior will be the same. Of course, the cubic function looks like this. And some examples of that, very similar to the quadratics, you could see a cubic written like this, or you could see a cubic written out like this. Another important function is the square root function. Any function involving roots, not just square root, of course, but functions involving roots are going to behave similarly to this one. The square root of x function looks like this. Remember, you cannot take the square root of a negative. You cannot take the square root of a negative, so negative values don't exist on this function, this function's domain. Some examples of square root functions might be the square root of the quantity x minus 1. You would need to focus there. When is x minus 1 negative? Well, I cannot input x values of those kinds into this function. You may also have it written like this, where we're subtracting 3 outside of the square root. So we're performing the square root operation on the expression x plus 2, and then we're subtracting 3. This, of course, shifts the function down 3 units and left 2 from this expression. But you could see them written in this form, and really you can have just about any type of expression beneath the square root. Power functions are also extremely important, and we have two cases of power functions or negative power functions, just like we did with quadratics and cubics. We have the odd negative power function. The parent function I like to refer to there is 1 over x. What I mean by odd negative power function is if I write this as f of x equals x to the negative 1, I can identify that this exponent is odd and negative. Odd negative power functions behave in the same manner as the function 1 over x. Behaves like this, where we have a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. You may see these functions written like this. Any odd negative power function is going to behave, again, exactly like this. It might be shifted in the plane, but the behavior is going to be the same. You're going to have those asymptotes. They might be moved in the plane as well. But also, a function like this is a odd and negative power function, negative 5. This function behaves in a similar manner as 1 over x, of course, shifted and scaled appropriately in the plane. 1 over x squared is almost identical, very, very similar. This is even negative power functions. Make note of the fact that we're squaring the x values in the denominator. When you square a number, regardless of whether it's positive or negative, we get a positive value there. So we're going to have a very similar graph to this, except we will not have these negative values at negative x values. We won't have negative y values at negative x values. We'll have positive y values. So this function looks like this. And any even negative power function is going to behave similarly to this. We could shift it up in the plane 3 units, but also we could have a fourth power. This would behave exactly like this one does, shifted and scaled appropriately in the plane. I'm going to state the domain and range for these two because this is really, really important when we get to our discussion of continuity. The domain of the function f of x equals 1 over x is all x values that are non-zero. Remember, you cannot divide by 0. This is very important. I'll refer to these as problem spots in lecture. 0 is a problem spot in this case. You can't divide by 0. Here, let's look at this one. The domain and range will change based on the value of the problem spot. In this case, x equals 2 is a problem spot. So 2 would be excluded from the domain of this function instead of 0. But the parent function has a domain and range, negative infinity to 0, union 0 to infinity. You could also write this as all real numbers such that x is not equal to 0 for both of these cases. The odd negative power function does have negative y values in its range. The even one does not. The domain and range of this function, domain is the same, the range is different. The range in this case is only positive non-zero y values. We're squaring that denominator, or raising it to a fourth power, or raising it to an even power. So we're turning negatives into positives here. Any questions about those? This is essentially all from college algebra. Once we get to the exponential, we're maybe approaching trig territory there, but any questions about those parent functions? All right, let's talk about the exponential function. The exponential function and the logarithmic function are what we call inverses of one another. We'll talk about inverses a little bit more in this lecture, but at this point in your mathematical career, I would expect that you're able to graph the basic parent function, the base e exponential function, and not just graph it, but identify this y-intercept. This is very important. Remember where this y-intercept is. Remember this function's behavior. This function does have an asymptote along the negative y-axis. That is specifically along the negative x-axis. Generally, we just say y equals 0 is an asymptote, but as this function gets smaller, more negative, we're going to approach the negative x-axis but never cross it. So the exponential function never takes on the value 0. The domain of this function is 0, or no, the domain is infinity to infinity, negative infinity to positive infinity. The range is 0 to infinity. Y cannot equal 0. We have an asymptote there, and it's not negative as well. The natural log function, remember, is the inverse of y equals e to the x. Sorry, let me go ahead and stick some examples up here as well. But make note that the base e exponential is not the only one, right? We can have 2 to the x or 4 to the x. It's going to behave similarly to this, same y-intercept there. But also be familiar with the negative base e exponential. This function looks like this. That moves that asymptote to the positive y-axis. We'll discuss shifting and scaling a bit in a moment. But the natural log function is the inverse of the base e exponential. And remember what happens with domain and range of inverse functions. The domain and range switch. So the range of the base e exponential is the domain of the natural log function, and vice versa. The range is the domain. And this function looks like this. And remember, graphically, a function's inverse is a reflection across the line y equals x. So this function looks like this, with the x-intercept at 1. And in this case, we have a vertical asymptote at x equals 0. Negative y-axis. You can add, this is a horizontal asymptote up here. Y equals 0 is a horizontal asymptote of the base e exponential. X equals 0 is a vertical asymptote of the natural log function. And this is, reflected over the line y equals x. We don't just reflect the graph, we reflect the asymptotes as well. Some examples here. We could have the natural log of x minus 1. We could also have other bases. Base 2. Natural log is implied base e. You could write this as log base e of x if you wanted to. But the ln there implies that it's log base e. Another important log is log base 10. You'll see this written as just log of x. No subscript there. So if nothing's written there, it's a 10. If the natural log is written there, it's a base e. And any other base will be identified. So any questions about the basic catalog of functions. These functions are functions that I expect you to be familiar with at this point. I expect you to be able to identify the appropriate parent function given a function like this as well. And there's some review of this in that first homework assignment. But if you have any questions about any of that, now is a good time. Okie dokie. On to our conversation of transformation of functions. Now, transformations of functions is very, very, very important. And again, if you want to do this class without a calculator, this is essential. But for a function f of x, if we want to shift it and scale it in the plane, we can do one of four things. We can multiply it by a, we can multiply the input by b, we can subtract c from the input, or we can add d to the function. Multiplying a function by a is going to scale the function vertically. The most important thing, though, that's happening here is if a is negative, we're flipping the graph over the x-axis. This is the key. Honestly, the vertical scales themselves, multiplying something by 2 or 4, it's important to recognize that that's happening, but when a is negative, it's really, really essential that you're able to recognize this as a flip over the x-axis. Multiplying the input by b is going to scale a function horizontally, but again, just as with vertical, flipping this over the y-axis when b is negative is really, really, really key, really, really, really important. You need to be able to recognize those flips specifically. Scales, I'm not quite as worried about if you identify them perfectly. That's not really the end of the world. Sketching the basic shape is what's important here. And this contribute the most to that basic shape. We'll see an example here in just a second. If we subtract c from the input, then we're moving the function in the x direction, left and right. If this c value is x minus c, we're moving it right. We're moving it in the reverse direction as you'd expect. So let's put a little star here. X minus c shifts right c units. Opposite of what you'd think. X plus c is going to shift left c units. Really important here. Opposite of what you'd expect. But d, adding d, does exactly what you'd think. Adding d moves the function up. Subtracting d moves the function down. Let's do an example. Let's sketch the graph of f of x equals negative x minus 1 quantity squared plus 3. What is the parent function here? Somebody tell me what the parent function is here.
Quadratic.
So identify that parent function, y equals x squared, which looks like this. We're shifting and scaling that pattern in the plane. And we're going to do so by applying these rules above to that parent function. I'm going to take a and multiply it by the expression squared, add d, and then within the input, I can multiply x by b or subtract c. That's going to tell me what direction I'm moving in x. In this case, we have negative 1 times x minus 1 squared plus 3. So what we have here is a equals negative 1, b equals 1, and c equals 3. B equals 1 because this negative is in our formula. You could call this a formula. It's in our procedure. It's in our expression. The negative matches. So the c value does equal 3. We're going to be shifting this function right 3 units. Or sorry, right 1 unit. up 3 units. And then this -1 for A flips the function over the x-axis. So the graph of this function will look like this. Now, right 1 unit, up 3 units moves the vertex of this quadratic from 0, 0 to the new vertex, which is going to be 1, 3. This is how I do it. I then find 1, 3, put my vertex point there, and then go back and reference my A value. Is A negative? Yes, it is. So this is a quadratic opening downward with a vertex at 1, 3. This is sufficient for sketching a graph of this function. I want to see the quadratic opening downward. I want to see the vertex, and you're done. Find those important points, like the vertex for the quadratic.
Doesn't matter how wide you make your graph.
No, that's what I mean. Like the vertical scaling and the horizontal scaling, it's not as important to me when you're sketching that graph that you identify it necessarily perfectly. What I want to see is that vertex in the appropriate place, and then for the case for the quadratic, it either opening downward or upward. For the base E exponential, I'd expect to see the intercept of that y-axis in the right place, and then just sketch that general trend of that exponential function, etc. Any more questions about shifting and scaling? Okay, next, inverse functions. Now, graphically, we already kind of talked about this. An inverse of a function is that function reflected over the line y equals x. But if we were given an expression for f of x, how would we find the inverse function? Well, for me personally, I like to just solve for x. Take the function and algebraically manipulate it to be a function of y. Solve for that x variable. You may have heard in the past, or may have done this in the past, where you switch x and y. For me personally, I don't do that right off the bat. I wait till the end. I wait till I get my expression for f inverse. Personal preference, if you're comfortable switching x and y and that's how you like to do it, no problem. There's many ways to do a lot of this math. And in general, I'm not opposed to allowing you guys to use alternative methods if you've learned those methods before, but I will dictate how I do it, and then, if you have a different method, if you're concerned about your method not being acceptable, send me an email, let me know. But generally, if you know a method for doing something that's a little different than mine, it's fine. You guys tell me, how would I solve this expression for x? What's the first thing I would do here?
Multiply y by x plus 1.
Yep. Multiply x plus 1 on both sides. This cancels on the right. X plus 1 divided by x plus 1 equals 1. So we have y times x plus 1 equals 2. What next?
Divide 2 by y.
Yes. Nice job. And then what? We're solving for x.
Subtract 1.
Yep. So we have the expression x equals 2 over y minus 1. Remember, we're inverting this function, so we're switching the domain and range. X is the domain of f. Now, y is the domain of f inverse. However, mathematicians really like to keep things consistent. When we name f inverse, we're going to turn that y into what we generally accept as an independent variable. We're going to write that as an independent variable. And it's also important to realize in math, you can name these variables anything you want to. Nothing is stopping you from calling this k if you really, really want to. I'm going to rename this y as x so that when I'm discussing the inverse function, I'm dealing with the appropriate variable for the domain. But in general, if you want to rename stuff, or say you're given a problem with variable a instead of x and you like x better, rename that variable to x and deal with that problem with the variable x. Just state that you're doing so. on tests. And if you're doing it in WebAssign, be really careful and make sure you input the answer with the original variable that it asked for. As well as WebAssign notices a difference between a capital X and a lowercase x. These two variables are not the same. So just be sure you're not entering in capital letters by accident as well. Common mistake in WebAssign. But what I have found here is the function who is the inverse of 2 over x plus 1. Now, we'll talk about function composition here a little bit, but don't forget, you can always check these by taking the composition in whichever order. You could compose f with f inverse or f inverse with f, following through with the algebra, and you should be able to simplify that down into just an expression x. We'll talk about composition in a minute. Again, graphically, and I'll illustrate this with the base e exponential and the natural log function. Graphically, when we invert a function, we're reflecting it over that important line, y equals x. So visually, graphically, if I plot the base e exponential, let's label it. That's another important thing when you're graphing something, please label, especially if you have multiple graphs or multiple functions on the same graph. Label those graphs. If it's just one, like above where we were talking about parent functions, it's fine. But label it if there's more than one. This is y equals e to the x with that intersect at 0, 1. Again, don't forget we have that horizontal asymptote along the negative x-axis. When we reflect this line over, or reflect this graph over the line y equals x, we obtain the inverse of it. And that's a really nice picture. I did great graphing today. I'm going to pat myself on the back. I'm usually really bad at these things. You'll see. I'm not great at graphing sometimes. Not great at drawing straight lines. That's okay. We have the natural log function, which intersects the x-axis at 1, 0. Notice how these two are flipped. 0, 1, 1, 0. Domain and range are switching, as well as that horizontal asymptote becomes a vertical asymptote, x equals 0 for the natural log function. That said, if I asked you to invert a function that was a log or an exponential, what would you do? And this is a great review of algebra with logarithms. So you need to review logarithm algebra. Come here. There's also some resources on Canvas as well to review this concept, but we'll do a quick example. If I asked you to invert the function y equals log base 3 of x minus 1, what would you do? Same procedure as before. Solve for x. Or alternatively, switch your variables x and y and solve for y, whichever one you prefer. I'm going to solve for x. Does anybody know what the first thing I need to do to solve this expression for x is?
Isn't it you have to change the log to like a different form? I forgot what the form is, right?
You do, you're correct, but wait 1 second. You do have this logarithm multiplied by 2. We have to isolate the log before we do that. So we need to isolate this expression. And then exactly what you said. So we're going to divide by 2. And then yes, we're going to treat this operation appropriately. This x minus 1 is captured in this logarithm. We have to treat this operation appropriately. Don't add 1 to both sides. This expression x minus 1 is captured in this logarithmic operation. We have to perform an operation to undo it, quote unquote, undo it. One thing you can do, if you're comfortable with this, is exponentiate. If you know what's going to happen when you exponentiate. For me, I like to reference I call it Ben, but this is the log rule for how to translate logarithms into exponentials and exponentials into logarithms. I like this acronym BEN. Base E raised to the exponent, or sorry, base B raised to the exponent E equals N, this exponential expression, can be translated into a logarithmic expression by essentially picking up that B, putting it in the base of the log, applying that logarithm operation to the number N, and it's going to equal that exponent. Remember what the logarithm's doing is essentially making a really big exponential function a little easier to deal with. But you can go in the other direction as well. If you have a logarithm of base B applied to an expression N equals a value E, we can go in the opposite direction. We can take that B, write it as the base, take that E, write it as the exponent, and set it equal to that value N. So here we have B equals 3. We have E equals y divided by 2. And we have N equals the expression x minus 1. Oops, that wasn't a highlighter. It's a pattern recognition thing here, or you could even think of it as a puzzle. I have these puzzle pieces in my logarithm. I'm going to turn it into an exponential. It is 3 raised to the y divided by 2 equals x minus 1. Again, we're solving for x, so we're going to add 1 over. So x is going to equal 3 to the y divided by 2 plus 1, meaning the inverse function is that function with x as the independent variable. And again, you can check this by function composition. Using rules of logarithms will help you here to simplify this down, to check and make sure that you get x. But this is the inverse of this function. Any questions about that? There is some homework problems for homework 1 that's going to require you to review this just a little bit, but this is a really useful thing to take care of reviewing now before we get too far into this class. Some of the stuff we'll review as we go, we'll come back to and discuss it maybe a little bit, but this is one of those that if you're not, if you don't remember how to do this, I would review this tonight, tomorrow, this week at some point. This will be a good one to check off the list and not have to worry about later. Next, function composition. So remember, function composition can be written like this, where you might read this as fog. This looks like fog, F-O-G. But this symbol indicates that you're dealing with a function composition. This reads f composed with g, f of g of x. And it's more clearly, in my opinion, written as the expression f of g of x. It tells you exactly what you need to do. If you know how to read it, if you know how to read the math in English. Here, we're taking the function g of x and treating it as the input of the function f. So everywhere we see an x in f, we must replace it with the expression g of x. Let's do some examples. If I give you f of x equals x squared plus 1 and g of x equals x plus 2, and I ask you to find the expression for f of g of x, then you could write f of g of x equals f of g of x. And then remember, this is exactly like evaluating a function at 2. You take the 2 and replace x with 2 everywhere there's an x in the f function, and then you do the arithmetic. In this case, we don't have arithmetic to do. We have algebra to do. Everywhere we see an x plus 2, which is g of x, or everywhere we see an x in f, we're going to replace it with the expression x plus 2. So There's only one x term there. So we're going to put x plus 2 in its place for x, square it, and then add 1. Now, I do want you to be comfortable simplifying these things. So let me ask you a question. Does this equal x squared plus 4 plus 1?
Yes.
Does it?
Actually, no.
Careful there. Yes, it doesn't. It doesn't.
You have to breaks into 2.
Yes.
There'll be a 4x2.
It would be x plus 2 and then x minus 2, right?
Yes. Don't distribute the square. Remember, when you have an expression, x plus 2 squared, this equals exactly what you just said, x plus 2 times x plus 2. You have to FOIL here. And it's okay if you didn't see that. This is a common mistake that I see in this class, and I'm specifically, talking about this so that you guys don't make this mistake. You have x plus 2 times x plus 2. You have to FOIL. X squared plus 2x plus 2x plus 4 plus 1. And I'll do things like this a lot. If you see stuff written in red in your notes, generally it's a red flag for common errors. I don't like to use red very often. I use it when it's something you really need to pay attention to. Don't distribute the square. X plus 2 squared does not equal x squared plus 4. It equals x squared plus 4x plus 4 plus 1.
Why wouldn't it be x plus 2, x minus 2?
Because we're squaring only this expression x plus 2. What you're thinking of is factoring.
Yeah.
X squared minus 4. This does equal x plus 2, x minus 2. But this isn't explicitly a square like this.
Right.
This, yeah, good question, good question. This is literally, you just take whatever you see written there and write it twice.
That makes sense. Thank you.
Similarly to something like 3 squared. Remember, this is 3 times 3, right? It's the same thing for x plus 2. Good question, good question. Good thing to distinguish between. And then again, be comfortable simplifying this algebraically. This is x squared plus 4x plus 5. We do need to add the 1 and the 4 here. Excuse me. Sorry. This would be the most simplified expression. And this is going to be a common conversation that we're having in this class. How far do I want you to simplify? You'll get comfortable, and I'll talk about it a lot. You'll become comfortable knowing what kinds of simplifications that I expect in this class. What I would say is, if you're not sure, if you're taking a test and you're like, I don't know if she wants that simplified or not. If you're not sure, go ahead and simplify it. If you're uncertain, safer to simplify it than to not. This would be something that I would expect you to simplify. Any questions there? Whew. I think we're probably going to take a 3 to 5 minute break at the top of every hour. This is lecturing for 3 hours. Is going to be very interesting. Next, what if I asked you to find f of g of x given these two functions? And actually, here's what I want you to do. I am going to change this problem. I'm not going to change the expressions. What I'm going to change is the name of the variables so that I can show you guys and illustrate to you guys that the name of the function doesn't matter. I can compose h with k here. If I say that h of x equals the square root of x plus 2 and k of x equals x squared minus plus 1. It doesn't matter what these functions are named. What matters is the pattern. This is h, which is on the outside to the left of the circle, h of k. Everywhere I see an x in h, I'm going to replace it with a k, with the function k. That is h of x squared plus 1. Everywhere I have an x in h, I'm going to write the expression x squared plus 1. So I have the square root of x squared plus 1 plus 3, 2. I'm not squaring this x squared plus 1. I'm just substituting there. So we can combine the constants. This is the square root of x squared plus 3 when we take the composition. Be really careful about these square roots. We have a similar common error with these square roots. Remember, the square root is an operation, excuse me, that is capturing this expression, in this case, x squared plus 3. The expression beneath that square root is captured. I can't do anything with this function until I evaluate x squared plus 3. Then I can take a square root. What I mean by that is the expression, the square root of x plus y, does not equal the square root of x plus the square root of y. This is really, really, really important. Don't distribute the square. Don't distribute the square root. Don't distribute powers where you have an expression captured within that operation. So be cautious about that. So don't rewrite this as the square root of x squared plus the square root of 3. That's not correct. This does not equal x plus the square root of 3. This equals the square root of x squared plus 3. That's our final answer. This is incorrect.
And how did you get to the 3 from the plus 2?
I have 1 plus 2 here.
Oh, okay. All right.
Since there's no like square happening here or any other operation that would require simplification, I can just combine those constants there.
All right.
So what did you say the square root of x squared plus 3 breaks down to?
The square root of x squared plus 3 doesn't break down any further.
Oh, okay.
Yeah, it's captured there. Where it might break down, or it might, a situation where you might see it simplify is if you have the square root of x plus 2 squared for whatever reason. This is x plus 2 squared raised to the 1/2. We're going to talk about exponent rules here in a minute. But the only way that you can quote unquote cancel that square root away is if you have a perfect square inside it. If that square root operation is operating on a perfect square. Thank you, Matthew. I see your DM. Thank you. That leads us into properties of exponents. Now, I cannot emphasize enough how important these rules of exponents are. They're very important in this class, but they're really important in Calc 2. If you have to take Calc 2, go ahead and review this now. Become comfortable with rules of exponents. Get it over with. Get it done. Do some practice because you're going to need it. It'd be beneficial for you to take care of any confusion you have about rules of exponents and logarithms at this point moving forward. But rules of exponents are as follows. For base x, note that the bases here have to match. We do have base x in all of these cases. The bases have to match, but if we have matching bases raised to powers multiplied together, we add the exponents. An example of this would be something like x squared times x to the 3rd. This is x to the 2 plus 3, which is x to the 5. Now, pro tip, if you ever forget your exponent rules, just don't forget what exponents mean, right? X squared means x times x. X to the 3rd means x times x times x. How many x's do we have in this case? Well, we can count them. 1, 2, 3, 4, 5, just as we expect in the answer that we have written here. If you ever forget your exponent rules, default back to what do exponents mean? 2 squared is 2 times 2. X squared is x times x. You can write them out. In more complicated examples, it gets really cumbersome to do this, so the exponent rules are useful. But if you forget, you can think back to this example. X squared plus x to the 3rd is x to the 5th because there's 5 x's there. This can help you remember that rule. Likewise for division, if I have base x to the a divided by base x to the b, I subtract the exponents. For example, if I have x to the 5th divided by x squared, This is x to the 5 minus 2. That's x to the third. But if you forget, again, remember, x to the fifth is x times x times x times x times x. X to the second is x times x. Think of this as a cancellation problem. X divided by x is 1. X divided by x is 1. So how many do we have left? 3, as expected. Also, if I raise a base x to a power of a and then proceed to raise it to the power of b, I have multiplication of exponents, x to the a times b. For example, x squared raised to the third power is x to the 2 times 3, which is x to the 6th. Now, I can't tell you how many times I've written down these two examples to remind myself of which exponent rule I need to apply for a given problem. I recommend doing that if you forget. In this case, if you forget, you can also use the fact that I'm cubing this expression, x squared, so I can write it down 3 times. And then remember what, x squared is. It's x times x. So I can go in and write out each factor and then count. Here I have, as expected, 6 x's, as I found there. It just helps us remember. 1, 2, 3, 4, 5, 6. These two examples really can be beneficial if you ever forget the difference between these two rules. These are probably the two that get confused the most. Even for me, I'm not gonna lie, I get these two mixed up sometimes. If I ever do, and I want to remind myself or verify and check, I think back to these two examples: x squared times x to the third versus x squared raised to the third. Two different answers. Also, kind of coming back to fractional expressions, if I have a base x to the power of a in the denominator of an expression, I can rewrite that as a negative exponent. So, for example, say I have x to the -1, we could rewrite that as 1 over x. But this rule is useful in both directions. Remember, you have an equal sign here. I can start with what's on the left and obtain what's on the right, or vice versa. Start with what's on the right and obtain what's on the left. So if I had an expression like 1 over x to the 4th, I could also simplify this to x to the -4th if I wanted to, for whatever reason. Generally, negative exponents are a no-go. You want to try to not have negative exponents if possible. Rewrite it in these expressions. But sometimes simplifying these things algebraically can be useful if you rewrite it as follows. Last, we have the rule that translates radicals, translates square roots, cube roots into exponents. Remember, the number that is written in the little v of our radical goes in the denominator of the exponent. If there's nothing written in the little v of the radical, it's an implied 2, otherwise it'll be written there. And then whatever power is on that base x inside that square root goes in the numerator of that fractional exponent. So for example, if I have y equals the square root of x, I could rewrite this as x to the power of 1/2. Or say I have the expression cube root of x to the 4th. I could rewrite this as x to the 4 divided by 3. Just remember what's in the v goes in the denominator of that exponent. Any questions about rules of exponents? Okay, let's do an example. Let's simplify the following expression. Say I gave you x squared times y times z over x times y times z to the fourth, all raised to the third power. Let's simplify this as far as we can. Let's group together everything. Remembering that these exponent rules only apply when the bases match. So we can only combine things in this problem, x with x, y with y, and z with z. So let's start. And I recommend for these types of problems where to start. Try to find the outermost expression, the thing in your problem that's being applied to the most stuff in informal language. In this case, we have this expression in the denominator being raised to the third power. The power of 3 is affecting x, y, and z in the denominator that are then going to affect x, y, and z in the overall problem. So simplify that outer operation, the outermost thing, the outermost power first. So to do so, I'm just going to rewrite the numerator as is. You can do this carrying through numerators and denominators. Don't try to do too much in one problem for problems like this. If I have x times y times z to the fourth raised to the third power, well, this is this example, but it's the cube applying to each piece. So we have x to the third, y to the third, and z to the fourth to the third. From there, I can then appropriately distribute, quote unquote, distribute this cube to x and y, as well as to z, but with z, we have to multiply 4 times 3. This is rule 3. So we have z to the 12th here. And then, well, we have x squared times y times z, drop in the parentheses because multiplication is associative. Now I have expressions of x in the numerator and the denominator, expressions of y in the numerator and the denominator, and expressions of z in the numerator and the denominator. So what I have here is x to the 2 minus 3 times y to the 1 minus 3 times z to the 1 minus 12. That is rule number 2. Leaving me with x to the minus 1, y to the minus 2, and z to the minus 11. All negative exponents, so let's write them in the denominator and make them positive. If you have a negative exponent in a denominator, same thing. Move it to the numerator, though, and make the exponent positive. This would be our final answer. This was rule 4. This will be your final simplified answer, all with positive exponents. Your homework 1 should have at least one problem for you to practice there. Laws of logarithms really are all derived from the laws of exponents. These are very closely related. They are really essentially the same rules. Just remember that log base b of n equals e can be translated into b to the e equals n. This is the BEN acronym. I'll refer to it as BEN, B-E-N, BEN. In my opinion, this is more useful than this expression because there's actually an acronym associated with it to help you remember. Either way is fine for me, but just remember that there is a inverse rule with logarithms and exponents. If I apply log base a to an exponential expression a to the x, they're inverses of one another. This does equal x. And likewise, if I have a raised to the log base a of x, I have x. If I have an exponentiation of log base a to the base a, I will have x as well. This is because these two functions are inverse functions. As well as there's two rules of logarithms where log of x times y equals log of x plus log of y. Again, almost a direct result of those exponent rules we just learned. And likewise for log of x divided by y, we have log of x minus log of y. Just be really careful about applying these rules appropriately. And then the power rule for logarithms is extremely useful. If I have a log of an expression x to the rth power, I can rewrite this as r times the log of x. This is one of those very useful ones that can come in handy in a lot of situations. All right, let's take 3 minutes. I need to get some water and use the restroom. So let's take 3 minutes and reconvene back here at 10:09.
Miss Cooper, can I ask you a question?
Sure.
So on Canvas there was like a quiz, I think it was due last week. It was like the were we supposed to know like the information? I didn't really understand.
The course information quiz should be due on the 26th.
No, it wasn't course information. It was, I'll go look what his exact name was.
That was due last week.
Yes, it was part of the to-do list.
Oh. Yeah, I put on you guys' to-do list for today, the course information page, just to remind you to view that before you take the course information quiz. Maybe that's what you're talking about.
No, it's maybe I just took an earlier quiz that wasn't due yet, but because I was like, I don't even know what this information is.
Okay, I think everybody pretty much is that.
It was like, I'll look for it and then I'll send you an email.
Yeah, that's fine. Do that. Yeah. All right, let's proceed into our geometry discussion, geometry and trigonometry. So the basic geometry of linear functions is really important in this class. So let's review that. Remember, a linear function has the general form y equals mx plus b. Any linear function, regardless of the way it's written algebraically, can be simplified down into these two components, m, the slope, times x plus b. And b is the y-intercept. It's telling you where that graph is crossing the y-axis. This is this is what's called slope-intercept form. Like I mentioned, regardless of how the linear function is written algebraically, it can be written in point-slope form. You can simplify it down into this basic structure, y equals mx plus b. If you just simplify it algebraically, get y on the left and all of your other expressions on the right, this will translate appropriately. Slope-intercept. This is what this is called, slope-intercept form. Now, if I give you a graph of a function, I'd expect that with enough detail, you'd be able to form this linear function, identifying m and identifying b. So if I give you a graph of a line that intersects the y-axis at 0, 3, but also crosses through the point 1, 0, then I'd expect that you'd either be able to count. That's not a straight line. See what I told you? I can't draw lines. I'd expect you to either be able to count, rise over run. We're going down 3 over 1 to get to our second point, or use y2 minus y1 over x2 minus x1 to find your slope. It's important to note that you can subtract in any order you want here, as long as you subtract in that order for both the numerator and the denominator. So if we do y1 minus y2, we need to do x1, come on Rachel, you know how to write, minus x2. In this case, either by counting or by using this formula, we obtain the slope m equals -3. And that y-intercept is essentially staring us in the face there. That's b equals +3. So the equation of this line is -3x plus 3. You could also use point slope form. Point slope form requires you still to identify the slope m, but what it allows you to do is substitute x1 and y1 with one of the points, and you're done. So after you identify that slope, all you would have to do is simplify down with one of the points, x minus x1. Pick a point. Whichever point you use it consistently. Use that x and y coordinate. Let's use 0, 3. So subtract 0 from x and subtract 3 from y. And there's your point slope form. If you simplify this down algebraically, you will obtain y equals -3x plus 3. Just do the algebra here. X minus 0 equals x, so you have -3x plus 3. Same thing if I asked you to create a line through these 2 points. Right there, you have your y-intercept. Use your formula y2 minus y1 over x2 minus x1 to find m. If for some reason you weren't given the y-intercept explicitly, like you're not given 0, 3, you're given like 4, 5 or whatever, and you're creating that line, remember to use the slope and the x and y coordinate to plug in all of those unknowns into your slope intercept form or whatever, and then simplify down to get your b. Alternatively, point slope form becomes very useful in a situation where you're not explicitly given the y-intercept, but I do want to see your linear equations for this class always written in slope intercept form. I don't mind if you use point slope form, but do the algebra to simplify it into slope intercept form. Any questions about that? All right, let's add the equation of a circle to our catalog of functions, as well as all the trig functions that we have seen in trigonometry and that we'll use in this class. First off, the equation of a circle. Now, notice that the equation of a circle is not a function as written, but the equation of a circle is a very important one. And this is the parent form, where in this case, the center of the circle is at 0, 0, and the radius of that circle is r. Now, if I wanted to shift and scale this function, I'm going to use very similar rules to those that I had in my transformations rules. They're really identical, it just looks a little bit different. Where if I want to move the center of the circle from 0, 0, say I want to move it to 5, 5. Well, I'll subtract 5 from the x and then square it, subtract 5 from the y and then square it. This moves my center to the point AB. Still though with radius r. And of course, if we have any other constants floating around, you might have an equation of an ellipse. We're not going to worry about that too much right now, but the equation of an ellipse can be, whoa, Notability just crashed. The equation of the ellipse can be derived in a similar manner to this. Oh boy, I hope I didn't lose anything. I did. It's all right. So again, remember, if we subtract a constant from x or y, that moves the center to that point. We still have radius equal to r, but ellipses work very similarly. We'll focus on circles for now. And the first circle that should come to your mind is the circle of radius 1, the unit circle, given here. I expect that you know how to read this unit circle chart and know how to use it. Knowing how to read it's important, but knowing how to use it is also extremely important. Remember SOH, CAH, TOA. That's sine of an angle theta. Sorry, it's SOH, CAH. Not sure why I wrote A. Is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. And tangent of theta is opposite over adjacent. And remember what I mean by opposite, hypotenuse, adjacent. We're talking about the triangle created at the angle theta, the right triangle created at the angle theta. This would be the theta, and the opposite side relative to theta is this side. Adjacent side, the one that's not the hypotenuse, that's right next to it, and then the hypotenuse. So in this case, we'd say that sine of theta, pi over 4, is equal to pi over 2. Cosine of theta, cosine of pi over 4 is square root of 2 over 2. And tangent of that would be sine over cosine, or opposite over adjacent. Square root of 2 over 2 divided by square root of 2 over 2. That is, or sorry, square root of 2 over 2 divided by square root of 2 over 2. That is equal to 1. Pi over 4 is not the only angle we could consider. We could do pi over 6 as well. It will work similarly. Just remember that theta is that angle off of the positive x-axis. So what angle measurement away from the positive x-axis are we? In this case, this angle would be 5 pi over 3 away from 0. That's the angle relative to that positive x-axis. Let's do some examples. Let's evaluate sine of 4 pi over 3. Now let me ask you a question. If you weren't sitting here looking at the unit circle, where we can clearly identify the angle 4 pi over 3, how could you remember where this angle is? For me personally, I like to compare the magnitude of the angle I'm considering with the important axes angles. So we have in this case theta equals 4 pi over 3. Well, you don't have your unit circle written down. You can't remember where that angle is. Recognize, first off, that this is bigger than pi. It's bigger than pi because pi is 3 pi over 3. So pi relative to this angle is 3 pi over 3. 4 pi over 3 is 1 pi bigger than 3 pi over 3. So we're bigger than pi, as well as 3 pi over 2. If we want to compare this angle to 3 pi over 2, what we would need is, well, a denominator that actually is useful. So a denominator of 6 would be useful here. So if I multiply 4 pi over 3 by 2 over 2, I'm left with 8 pi over 6. If I multiply this angle, remember this is our reference angle, reference angle to our given angle. Trying to determine what quadrant we're in. We're comparing 9 pi over 6 to 8 pi over 6. This is 1 pi less in the numerator than 270 degrees. So we're somewhere in the third quadrant. Now the sine of the angle is going to match the sine from the first quadrant of the corresponding first quadrant angle. In this case, the corresponding first quadrant angle is pi over 3. So essentially, in this quadrant, we're pi over 3 radians away from pi, the negative x-axis. So we have the points matching the angle that's pi over 3 away from the positive x-axis in reference to our first quadrant with different signs. In the third quadrant, we have negative x values, negative y values. So the sine of 4 pi over 3 is the sine of pi over 3 with the appropriate sign, SIGN. So sine of 4 pi over 3 equals square root of 3 over 2 negated. Similarly for cosine, we don't need to compare this angle again. Cosine of 4 pi over 3 is cosine of pi over 3 negated. Hopefully this helps you realize you only have to remember the first quadrant. But when asked to evaluate sines and cosines or trig functions of angles that are not in the first quadrant, you do need a reference angle. You need to figure out what quadrant you're in as well. Also, don't forget that you can think of the unit circle as a pizza or a pie, right? We're looking at 4 pi over 3. This means that we have moved pi over 3 away from the positive x-axis 4 total times. This is once. This is 1 pi over 3. Be careful here because these angles, this angle and this angle are not equidistant. This is another pi over 3. That's 2 pi over 3. This is another pi over 3. 3 pi over 3. 3 pi divided by 3 equals pi. So we're at our angle pi. And then we have one more piece of pizza to get to 4 pi over 3. The same thing works with pi over 6. Just be really careful with pi over 6 because remember, pi over 6, this is 1 pi over 6. This is 2 pi over 6. This is 3 pi over 6. This is 4 pi over 6, 5 pi over 6, 6 pi over 6. Just be careful about counting the correct slices of pizza if you're thinking about that in terms of pizza. And just be cautious because this distance and this distance are not equal. This arc and this arc do not have the same length. So orange arc is not equal to the red arc length. Any questions about basic uses of the unit circle? All right, now don't forget that we can graph these trig functions. And when we graph trig functions, we're relating the angle of interest to the sine or cosine value, whichever one we're talking about, or tangent, whichever one we're talking about. So if I take the angle and I make a chart for each angle on the unit circle, what is the sine value? And I graph it, it looks like this. Sine is the function that passes through the origin at angle 0. The sine is 0. And then, of course, sine and cosine have the same kind of pattern. We have this oscillatory behavior. but the sine function is the one that crosses 0, 0. This is y equals sine x. Cosine is the same, but it crosses through the point 1, 0, 1. We have the same oscillatory pattern. In fact, sine and cosine can be shifted to be the exact same function. They really are the exact same function, just shifted in the plane. This is y equals cosine x with the intercept of 0, 1. If you forget, look at your unit circle. At angle 0, cosine is 1. And remember, we list the points, the x, y pairs, cosine, sine. Cosine, sine. The tangent function is the ratio of sine over cosine. And this function has asymptotes because at angle x equals what do we have a problem spot? Well, when the cosine function is 0, we're going to have a problem. We can't divide by 0, so we need to exclude these values from the domain. Quick look back up at our unit circle. Where is cosine 0? Pi over 2 and 3 pi over 2. It is the case that the tangent is undefined at odd multiples of pi over 2. So tangent is undefined for x equals 2k plus 1 times pi over 2. This says odd multiples of pi over 2. For k equals -2, -1, 0, 1, 2, 3, all integer values. This means that at negative multiples of pi over 2, we have undefined tangent. Undefined tangent means we have what? What kind of asymptotes? Vertical. When you sketch this graph, it's okay to just like identify one or two of those asymptotes. I generally plot negative pi over 2. That's -1 times pi over 2. It's an odd multiple of pi over 2. And positive pi over 2. And I try to fit 3 pi over 2 in there. This is going to be a little bit not to scale, but that's all right. Tangent passes through the origin because sine of 0 is 0. And this function is the one that looks like this. You can apply all of your shifting and scaling rules to these functions as well. Remember that sine and cosine, well, all of the trig functions really are periodic. So if you move them a certain distance, they're identical to before you move them. That is pi over 2 is the period of sine and cosine. The period of tangent and cotangent is pi. Last, we have the cosecant, secant, and cotangent functions. Remember, cosecant is 1 over sine of x. I remember this because cosecant starts with a c. My options are sine and cosine, while sine doesn't start with a c. So it's the one that's in the denominator of the cosecant function. Similarly, secant starts with an s. Cosine's in the denominator because cosine does not start with an s. And you can think of these functions, it helped me the first time I ever saw these, to think of these functions as every point in the plane that the sine and cosine functions respectively did not capture. So the sine function looks like this. Cosecant is going to look like this, where of course we need to be careful about when sine is 0. We do have asymptotes when sine is 0. Sine is 0 at 0, sine is 0 at pi, etc. Period of this is pi as well. So we're going to have asymptotes at every pi interval for this function. And again, this is capturing the pieces in the plane that the cosine function is not. So the value of intersection here is 1. That's the only common point there. And likewise for secant, just be really careful. Secant is undefined where cosine is 0. cosine is 0 at negative pi over 2, pi over 2, etc. So secant has the same asymptotes as the tangent function did. I'll just graph these two, but let me leave myself some space on the other side. So the cosine function is the one that starts at 1. So stuff like this, and it's going to fill in the plane everywhere the cosine function wasn't. And that, of course, repeats. Cotangent as well. Cotangent is 1 over tangent, which is cosine over sine. For cotangent, it's the opposite. C goes on top. And of course, this is going to be undefined where sine is equal to 0. We're going to have asymptotes at x equals 0, x equals pi, x equals 2 pi, 3 pi, 4 pi, every multiple of pi in this case. And cotangent goes downward. And don't forget what we're plotting here. The x-axis is the angle. The y-axis is the value of cotangent at that angle. So if you ever forget that the cotangent function is decreasing, go back up to your unit circle and cross-reference those values. You can't apply all shifting and scaling rules to any trig function. Just keep in mind that they're periodic. Again, the sine function has period 2 pi. Likewise for cosine, secant, and cosecant. Tangent and cotangent have period pi. So if I pick up the sine function and shift it to the right 2 pi units, I'm essentially left with the exact same function as I started with, the sine function. Any questions there? Okie dokie. Next, as a bonus, good point to talk about this, inverse trig functions. So consider f of x equals sine x. If we were to invert this function. Now, be really careful about inverting functions because it's only possible to invert a function that passes the vertical line test. For inverse functions, it's vertical line test. Because when you invert it, you're turning those vertical lines into horizontal lines. You need to ensure that the function you end up with is a function. The inverse of sine has to be a function. It's not possible to invert it otherwise. So we have to carefully restrict the domain of the sine function in order to invert it. So how do we do that? Well, generally in mathematics, we're going to restrict sine, cosine, tangent, etc. in a very specific way. It's generally accepted that these functions are restricted in a certain way across the board, and we will use that reference, that frame of reference for all inverse functions. So let's plot a quick sketch of the sine function and consider what intervals we may be able to restrict the sine function to and still invert it. So notice if I flip this function over the line y equals x right now, it would not be a function. It would look like this. That doesn't pass the vertical line test. So in order to invert a function, we have to restrict it in such a way that it does pass the vertical line test. Well, we could restrict it here. We could restrict it even here. But generally, the sine function is restricted here to invert it. So to invert sine, restrict the domain to -1 to 1. When we invert it, we obtain f inverse of x equals sine inverse. It's either going to be denoted as sign with a little -1 in the exponent. Please don't raise sign to the actual negative first power. This is only notation. To avoid that confusion, I prefer using arcsine, arccosine, arctangent, etc. when talking about inverse trig functions. So if we restrict it as such and we invert it, then we have that graph of that inverse sine function that you're used to seeing. So we're going to reflect this over the line y equals x to have that graph. Likewise, for the cosine function, we have to appropriately restrict the domain. And it's important to notice that I could have restricted the domain here. I could have restricted the domain there. As long as I restrict it in a way such that when I reflect it over that line, y equals x, I have a function, you're okay. But again, generally accepted in math across the board, we're restricting it between -1 and 1. Cosine's different. Cosine's going to be restricted between 0 and 1. Oh no, it's going to be restricted between -1 and 1, but the range is going to change. In this case, the cosine function looks like this. We will restrict our domain here to invert the cosine function. Why do my notes say it's -1 to 1? Oh, no. We're restricting the domain of cosine to 0 to pi. The range is -1 to 1. The domain becomes that. So restricted domain for cosine. Do you need to say something?
No. No, I was just going to help you.
I'm good. The restricted domain is 0 to pi. So notice if we restrict it like we did with sine, if we restrict it here, let me get a different color. Let's do red. If I restrict it here, this piece of the graph does not pass the horizontal line test. So that you can't restrict it there. You have to restrict it in a way where it passes the vertical line test. For the case of cosine, generally accepted to restrict between 0 and pi. We can restrict anywhere where we end up with a function that passes the horizontal line test. But when you see cosine inverse, you can assume we're restricted the cosine domain to 0 to pi. And then remember, the domain and range switch. So what was the domain of the restricted cosine function becomes the range of the cosine inverse function. This will give us f inverse of x equals arc cosine of x. Again, I'm going to use arc cosine, arc sine. I'm not going to use this. This can lead to way too much confusion with squares and cubes and everything. So we'll use arc sine, arc cosine. Likewise for tangent, it's a little bit easier to restrict the domain of tangent. As long as you restrict it on an asymptote or between asymptotes, between appropriate asymptotes, then you're good to go. You can restrict it on any asymptote you'd like, just the tangent function or arctangent function generally accepted as restricted between -pi/2 and pi/2. Again, remember, this is periodic. We have this repeating over and over and over again, but to invert it, we are going to, sorry, I don't want to write that in red. We're going to restrict to the domain to -pi/2 to pi/2. For arctangent, that's the range, of course. And this gives us the arctangent function. The same thing applies for sine and cosine. Of course it does. Same thing applies for secant, cosecant, and cotangent. This would be where we restrict the domain. You could, again, restrict it over here and obtain an appropriate inverse function. You just have a different range. Any questions about that? If you want to see these graphs of what they look like, I mean, again, they're just a reflection of this piece of the graph over the line y equals x. Reflection of this piece of the graph over the line y equals x. You can take a look at those if you'd like to. Just a quick Google search will give you those images. But the main point here being, in order to invert these functions, you have to restrict the domain. And it's actually interesting. We've really done this already. When we invert the function y equals x squared, we restrict the domain. Because remember, you can't take the square root of negative numbers, so we almost just ignore negative x values in the x squared function. And when we invert it, we only invert that piece of x squared that's positive, because otherwise it wouldn't be a function when we reflect it over the line y equals x. Not really anything new, just maybe a different way of looking at it. Question?
So I get the rules for restricting domain, but can you clarify what exactly that means?
It just means that in order to speak to the inverse function, we have to make sure we're only considering portions of sine and cosine that are appropriately translated. And again, just some mathematicians one day in the past decided this is how we're going to restrict the sine function to discuss sine inverse across the board, so that we avoid any confusion of someone speaking to whatever other set of angles you might be interested in. The translation of the inverse trig functions is best illustrated by example here. So if I ask you to evaluate arc sine of square root of 2 over 2, what exactly are we asking for? What exactly are we saying? Hopefully this will clarify your question. Let me know if it doesn't. How this reads is, arc sine of square root of 2 over 2 is asking, so if we say this equals a value, let's let it equal k. What this says is k is the angle whose sine equals square root of 2 over 2. Again, emphasizing the restricted domain thing here, go back up to your unit circle and tell me how many angles you can see on that unit circle that have a sine of square root of 2 over 2. How many angles have a sine of square root of 2 over 2? Well, we have one right here, and we have one right here. Restricting the domain of the sine function in order to invert it tells us that this is not the angle we're considering. We're considering only angles here. So only the value pi over 4 can be the angle that we're talking about. It can't be this one because we've restricted the sine domain in an appropriate way. Otherwise, the answer would be, oh, I don't know, pi over 4, 3 pi over 4. I could keep going. I go around the unit circle 2 pi units and then continue up to pi over 4. I've got a different angle. I've got 2 pi plus pi over 4 with the same sign. Which sine angle, or which angle do I care about? Well, restricting the domain allows for us to know what angles we're talking about. That's important. I think I might have mixed up the sine one as well. Yeah, I did. Be careful here. I mixed this up. I put the range. We're restricting sine actually to negative pi over 2 to pi over 2. This is the range, -1 to 1. Restricting the domain is where the important angles are then going to follow through. So this is not right. This is the range.
I think you were putting the domain and range of the inverse function, weren't you? Or no?
This is the restricted domain of sine that allows us to invert it. So this would be the range of the inverse function.
Yeah, I'm just saying I think that's how you wrote it down.
Yeah, I wrote down the range first here. This one is right. This one was negative pi over 2 to pi over 2. Again, this tells us, looking at the unit circle, this tells us what angles we don't care about. We only care about the angles from negative pi over 2 to pi over 2 when talking about sine inverse. This is a valid answer, but if it were an answer, then sine inverse wouldn't actually be a function. So this is the only possible answer. This allows us to have only one possible angle answer for an inverse problem, for an inverse sine problem, as opposed to infinitely many, really, is what that is. Does that answer your question?
Yes, thank you.
Perfect. K equals pi over 4 is our angle whose sine is square root of 2 over 2. And it's technically the only one because of the restricted domain of sine. So this reads, arcsine of square root of 2 over 2 reads, which angle has a sine of square root of 2 over 2? The answer is the angle. The domain of the sine function, the inputs of the sine functions are angles. The outputs of the arcsine functions are angles. The output of the sine function is that point on the unit circle. The input of the arcsine function is that point on the unit circle. Similarly, for tangent, arctangent of 1 is equal to, let's call it m. Now let's not use m, let's use p. P is an angle, the answer is an angle. What angle has a tangent of 1 on the restricted domain of tangent? Well, look up at your unit circle. Sine over cosine must equal 1, so sine over cosine must equal each other. This is also pi over 4. But it's important to realize that there are other angles technically on the unit circle where that holds true. This holds true with this angle as well, but this is not in the domain. This angle is not, or this value is not in the domain of the arctangent function. Only values between negative pi over 2 and pi over 2 are. So the only angle that we could consider for the answer is pi over 4. Similarly, if I had asked you to find tangent of negative 1, this is the angle whose tangent is negative 1. So sine and cosine need to be the same, but 1 needs to be negative. And again, only on the interval negative pi over 2 to pi over 2. Take a look at your unit circle. Which angle is that? That's this one, 7 pi over 4. However, because 7 pi over 4 is this angle, when we discuss this angle in terms of the domain of arctangent, we're going to call it negative pi over 4. It's going negative pi over 4 radians from the positive x-axis down to obtain negative 1 for the tangent. Negative pi over 4 is in the domain negative pi over 2 to pi over 2. 7 pi over 4 is not. Very, very, very fine point there. I'm honestly not even sure if I'd make a huge deal about that. But it's more precise to translate it, quote unquote, translate it into a value that's in that domain. Okay, so there we go. We're done for the day. Nice that we got through that. Please go ahead and take the course information quiz so that you can access the Unit 1 module in Canvas and get those notes for tomorrow or Wednesday. We will start with Lecture 1 on Wednesday, and that will get us into our calculus material. Any questions before we wrap up?
Yes. So the quiz that I was talking about is called Quiz 6 Spring 2021 Math 200.
Let me check on that. It's possible that a quiz got moved over from a different semester and I missed it.
Yeah, it says it was due Wednesday, March 17th.
Yeah, no, anything that's due prior to now, just ignore.
I was like,
Oh yeah, no, that quiz 6 shouldn't even be posted. That's just a copy of the quiz that will be quiz 6 for you guys. I'll remove that. That is pretty confusing. I apologize for that. Where'd it go?
there's additional prerequisite material as well, and if you guys finish your quiz and open the first module, that additional stuff, that's stuff that I can go over in our first help sessions if you guys want, because I doubt you'll be starting your homework by tomorrow. But if you
Miss
do and you have
Cooper,
homework questions, you can ask that in the help session either tomorrow or Thursday.
Miss Cooper, I also have another question.
Mhm.
So I saw the textbook on Amazon, but it was the online version. Does it specifically have to be bought on the Reynolds thing?
It doesn't have to be bought from the bookstore, but what you do have to have is access to that WebAssign homework interface. So you can buy like a hard copy of the textbook off of Amazon if you want to, but at some point you're going to need to purchase that WebAssign access for the 11th edition, even if it's just a standalone WebAssign access.
Okay. Okay.
And buyer beware if you buy it anywhere else other than through our bookstore directly from the publisher. That's all I'm going to say about that.
Make sure you get the 11th edition WebAssign if you buy it from a third party. Cengage and Reynolds don't cover third party purchases. If you purchase it through the bookstore or the Cengage website and something goes wrong, they'll be able to help you there. But not if it's a third party purchase.
Like,
just be really, really careful if you buy it from a third party. Make sure you're getting that 11th edition.
And make sure you're not getting the international edition, which is not supposed to be for sale in the United States.
But what you're saying, it wouldn't really make sense because the Cengage comes with the textbook anyways.
Yeah.
And you'd have to get anyways, right?
Right.
Well, so you can purchase a standalone WebAssign access for one semester, to standalone WebAssign separately. Honestly, especially if you have to take this class, take Calc 2 and 3 at Reynolds, I recommend buying the ebook version. That's going to be the most convenient. But I mean, I haven't done much cost analysis in terms of buying a hard copy and purchasing WebAssign, but you can do that.
I think new editions of the textbook from the bookstore, if you buy it new, come with the access code for WebAssign included in them. I think they're bundled. Have to check into that, but usually if there's a online homework option for the textbook, when you buy a new textbook from our bookstore, it comes bundled with an access code, but not when you buy used.
By the way, we are done with class. If you guys want to head out, feel free. If you have any questions and you want to stick around and ask them, you may do that as well. You're welcome. Have a great Monday, guys. I'll see you guys on Wednesday. We will have breakout groups on Wednesday, but it'll be more towards the middle of class probably.